Welcome back, everybody. Our next speaker is Atsushi Hori. The title of his talk is On the Difference Between Shared Memory and Shared Address Space in HPC Communication. Prof. Hori?
Yes. Can you hear me?
Yes.
Okay, thank you. So I'm Atsushi Hori at the National Institute of Informatics in Japan. So I'm going to present a talk titled On the Difference Between Shared Memory and Shared Address Space in HPC Communication. So the shared memory, oh, no. So this. Come on. Next slide. Okay, so the shared memory and shared address spaces, space are the name of the memory model. So models. So we assume that there are multiple execution entities running on a multi or many core architecture and running on the same node, sharing the same physical memory. So we also assume that those multiple execution entities exchange information among them in some way. So what is the memory model means here is how an entity accesses the data owned by the others. Okay, so they share the same physical memory, so basically they can access the data of the other execution entity. Yeah, okay, so here in this talk, the execution entity is a process. This definition is in this talk. Oh, right. So, but in general, it can be said. Anyway, so there are two memory models. One is shared memory, and another is shared address space. The shared memory is widely used. It's very well used. So in the implementation of internal communication of MPI. Okay, so, but there are another memory model, shared address space, which is relatively new. Okay, so, but many people are confused those two memory models because both models allow to access data owned by the other processes. Okay, so but the mechanisms behind the scenes are quite different. So, and I'm very sorry to say that this talk is not to propose a new idea or new optimization techniques, but this talk is to clarify the differences of those two models, because there are big confusion, right? So many people in this session, listeners in this session are not familiar with the shared address space, but I'll come back in a minute, but before this explaining the shared address space, I talk about the shared memory model. So there are two famous techniques. One is POSIX shared memory, and another is XPMEM, cross memory attach. So in the POSIX shared memory, say an MPI process wants to send a message to the other, the sender firstly allocate a memory region and receiver attach that allocated memory region by sender to share the physical memory. So to do that, the sender and receiver have to call the mmap system call. And the XPMM, which allows a process to access the data owned by the other process. So but unlike the shared memory, XPMM allows to access the existing memory, right? So, but to do that, XPMM kernel module should be loaded, and to attach or to publicize a memory region, you have to call several IO control system calls. So both, POSIX shared memory and XPMM incur non-negligible overhead for setting up. Okay, so the shared address space model. It's a little bit hard to explain, but it is. So here's the example of a memory map. Okay. Okay. So in this example of the memory map, there are 3 tasks running. Three tasks derived from one program are running and sharing the same address space. As you can see, there are 3 programs, and there are 3 glibc mappings. And right, so here I say tasks for the shared address space, just because process I may use the term process, but strictly speaking, the process can be defined as sometimes process is defined as address space. But as you can see here, there are 3 processes running and sharing the same address space. So that's violate the definition. So I use the term task here in my talk instead of process. Anyway, right. So there are differences. As I already said, in this shared memory model, there is a certain overhead to create or attach a shared memory region. And also the mapping addresses of the shared memory region of a shared memory region may vary process to process. Okay, that means if the memory region contains some complex structure, such as a tree or list, then the another process cannot access the complex structure as they are. So it should be converted to offset or index instead of pointers. But in the shared address space model, any data can be accessed without any operation just because they share the same address space. There's no overhead. And also, all data can be accessed by any at the same. So any data in the shared address space can be accessed at the same address. I mean, it does not vary process to process. A structure A, the address of a structure A, it can be accessed from any tasks in the shared address space model. So this nature is called consistent address view, CAV, in this talk. So you can access the complex data structure as there, as it is. So without any modification, no need of conversion to offset or index. So here is the behind the scenes of those two models. The left-hand figure showing the page table structure, sharing a memory by using the shared memory technique. So here page table is I should say that address space is essentially page table inside the kernel. So the page, all the mapping information of the logical to physical memory listed in the page table, right? So the page table essentially a set of page table entries. So each page table entry has the information to map a memory page, physical memory page to be accessed in the virtual address space, virtual address. Okay, so but when to create a page table entry, okay, so no. Firstly, you may say that, okay, I wanna share this page, memory page. So I want to create this memory page to be shared. Then the kernel firstly create its skeleton, just skeleton. So when the process firstly access that memory region, memory page, then the page port, minor page port happens, and the actual page table entry is created at that time. So right hand, so on the left hand side figure, shared memory model, each process has its own page table, and to share a memory, physical memory, each page table entry should have a sub-page table. I'm sorry. Each page table has to have the sub-page table to access that shared memory. Okay, that means the page port happens on every process. But on the right-hand side, in the shared address space model, tasks share the same page table, just one page table. And that means page port happens once, but once is enough. So once a page table entry is created, that page table entry is used by all the tasks sharing that shared address space. Sharing that address space, sorry. Okay, so, okay. Right. Okay, so this is the same thing I already told. So there are pros and cons of shared address space. And pros are there's no need of special operation, such as the shared memory creation or shared memory attach, and there's no overhead to share data. And as already I told you, complex data structures can be accessed are there. So even the code can be shared. A task A may call a function defined in task B. So anyway, so, and as I told you, a page fault happens only once, regardless to the number of sharers. And as again, in shared memory model, page fault happens on every process. Cons. So to have the shared address space, there is you have to have a special environment requirement at this time. So, and there could be some confusion over here when changing the page table, just because that page table is shared among tasks, and so the changing means when you call, for example, mmap or break system calls to allocate or deallocate memory pages. So that could be slower than the shared memory model. Okay, so there's pros and cons, and how those pros and cons affect the performance of MP application. That is the objective of this talk. So to implement shared address space, we developed process in process, or PIP in short. So we developed this PIP, and there are several shared address space implementations, but the PIP has a very unique feature. It is a user-level implementation, so you don't have any special OS kernel or any special kernel module. You can run PIP programs on any hardware, any machines, any systems. So the implementation of PIP is utilizing the Linux clone system call and the DLM open glibc function. So you may not familiar with DLM open. So this is very similar to DL open to load shared library, but the DLM open can load a program or a shared library and it can create a new namespace. So that is the difference between DLM open and DL open. So but to load a program by calling DLM open, the program must be compiled as PIE, position independent code. This is very similar to PLC, which is used to create a library, but the PIE is to create a program to be loaded at any address. Anyway, so evaluation. Oh, this version is. This slide is older version, so this has somehow misaligned. Okay, so I use image 3.4.1. We have 4 configurations for this image. One is shemem, which is a baseline and the evaluation result. And the second one is XPMM. Here, the shemem and XPMM are using the shared memory model. And there's another two configurations, PIP shmem and PIP XPMEM. PIP shmem is the PIP version of shmem, but the MPI is the same. So the difference between the PIP shmem and PIP shmem and shmem just PIP shmem is with PIP shmem the MPI processes runs as PIP tasks. So we modified the MPH's Hydra process manager to create PIP tasks instead of POC and exec to create a processes. So anyway, so in the PIP shmem and PIP shmem are basically the same. And there's one big difference between XPMEM and the PIP XPMEM. So okay, so as I said, to have the shared memory region, it has certain overhead to create and attach. And the overhead, the XP and the MPH implementation, MPH XPMEM implementation has a XPMEM cache to reduce that overhead to attach to create and attach. But the PIP XPMEM, so as I said, there's no need of doing that. So in the PIP XPMEM configuration, that XPMEM caching system is bypassed. So this is just a comparison for the shared memory model and shared address space model. There is no further optimizations. So it is possible, but I intentionally do not apply any further optimizations. So those are just a difference. So okay, so I don't have. So this is the inter-MPI bench exchange benchmark result. Y-axis is the relative performance to shmem, and then the XPMEM and PIP XPMEM behaves almost the same. Okay, that's good. Here, this is the inter-MPI benchmark, RMA operation, output all on a single node. Again, the y-axis is relative latency to shmem. Here in this benchmark, PIP XPMEM is better in this message size region. Okay, that's good. Okay, so this is another inter-MPI benchmark result. This benchmark is to measure the latency to create an RMA window. So here, PIP shmem and PIP XPMEM, the latency creation time is the almost twice of those ones of shared memory model. Oh, that's not good. Okay, so I also run some mini apps, HPCCG, mini Ghost, Lules 2.0, mini MD, mini AMO, and the MPI graph. Here's the results. This left-hand side graph showing the performance, relative performance to shmem running on a single node, and right graph is the same graph but running on the multiple nodes. So as you can see, left-hand side, the PIP performance better than PIP XPMM performs better than XPMM, shared memory XPMM. Almost 1.5, roughly speaking, better. And okay, so the MPI, so this is the MPI graph application, and why MPI graph is so better. So here I measured the XPMM cache statistics, and I also measured the number of page ports. So on the left-hand graph on the left-hand side, showing the XPMM cache statistics, and the rightmost one is the graph bars of MPI graph. Upper bars in blue bars indicate the number of cache access of XPMM cache access, and the lower bars, red lower bars indicate the cache miss ratio. So here, as you can see, the cache miss ratio of the MPI graph is worst among the other applications. And on the right-hand side, and MPI graph again, there's a huge amount of page fault happens when using the XPMM. But if you use PIP XPMM, the number of page faults is far less than the ones of XPMM. So the high ratio of cache miss and high number of page faults results in the depth performance difference, I guess. So so far, so the shared address space may be a good choice for implementing a better intra-node communication such as MPI, but it is not. So one of the co-authors, Ouyang, is eagerly working on MPI implementation using PIP, and he is proposing some techniques by the communication steering or progress steering to have the better performance for the internal communication. Yeah, so in those techniques, the CAB nature of which provided by the shared address space plays a very important role. So summary, so I explained about the differences between shared memory and shared address space. And I show some results, people aware and page, and PPXPMM performs better in some cases. So that's all.
Thank you so much.
Any questions?
I didn't see any questions.
Wow. Okay.
So let's thank Prof. Hori again. Thank you.
Thank you.
Okay, our next speaker. Our next speaker is George Marco Manolis. He'll be speaking about the evaluating GPU programming models for the Lumi supercomputer. George?
Hello. Can you hear me?
Sounds good.
Okay. Oh, the slides are another version. I have uploaded a new one. Okay. So basically, this is a collaboration. Have done is a broad collaboration with HP, AMD, University of Heidelberg, and HZDR, Casus, and Georgia Tech. It's about evaluating GPU programming models, and because a new supercomputer is coming to Finland, and the outline is I will mention what is LUMI, the programming models that we are discussing, the porting workflow for the applications, and benchmarks and applications, hardware that was used, and results. So what's LUMI? LUMI is a new Euro HPC supercomputer. It's close to half exaflop and is constituted by many partitions. In this talk, we'll discuss about GPU. So we'll mention about the GPU partition, which is close to half exaflop based on AMD Instinct GPUs. But also there is a CPU partition and also slingshot interconnection and many storages, flash-based, self-encrypted, etc. So basically, here is a mock-up of the GPU that we use. This is the one that is not the one that's on Lumi, it's a previous generations. What you can see is that here it has 8 shader engines with 16 compute units each of them. So there are totally 128 compute units, but only 120 are available. This is important because we use this metric to tune some codes. And also in CUDA, in GPUs, NVIDIA GPUs, there is the concept of warp 32. Here is called wavefront and it's 64. So this is another aspect that needs to be considered when we develop applications about the things. Now, the programming models have the HIP. HIP is heterogeneous interface for portability. It's developed by AMD. It's a C++ runtime API and supports both AMD and NVIDIA platforms. HIP similar to CUDA, and there's no performance overhead. And many well-known libraries have been ported to HIP. And also, if you know CUDA, you know HIP. For example, the CUDA malloc is like HIP malloc, etc. And there are HIPify tools that convert CUDA codes to HIP, and it's quite efficient. Now, the OpenAP offloading. OpenAP is really well known, supports GPU since version 4. For AMD GPUs, we use the AMD OpenAP compiler, AOMP. And probably have here the ROCm, the main ecosystem from AMD, but AMD OpenAP usually has the latest upstream about OpenAP features and improvements. And here is an example of a Pragma OMP target, how you use the teams to distribute the workload on the GPU, and you need the SIMD for the Cray compiler, transferring to the memory. I want to mention the num_teams is about the blocks to have. So we have 120 compute units. So this is usually a multiply of 120 for MI100 GPUs. And the thread limit, here is the threads in the block that for MI100 is a multiply of the 64. 256 usually is a good number, but depending on the GPU and the software can be, and the code can be also a bit different. Cyclic is really now becomes a really known programming model. It's open standard for heterogeneous programming. It's developed by Kronos Group. You can express with pure C++ heterogeneous data parallelism, and it relies C++ 17. And starting on Cyclic 2020, it supports a lot of backends, OpenCL, Level 0, CUDA, HIP, and others. We can use data parallel kernels, the execution organized by task graph. A task graph can decide some communication depending on the model, and they have different models, buffer accessors, and unified shared memory models. And for this work we use the HIP cyclic implementation. There are many implementations, but HIP cyclic supports the AMD GPUs, also NVIDIA GPUs, and Intel GPUs now. Now, COCOS is a quite well-known framework for funding from ECP and NNCA. It's about writing C++ portable applications targeting all major HPC platforms. It provides abstractions for both parallel execution of the code and data management. And so basically, there's a layout that you can map depending on the hardware. You want the serial, you want to have host parallel, OpenAP, device parallel, but also there's about memory layout, execution policy, static dynamic scheduling, thread teams, and also parallel for reduction, etc. Now, the OpenCC, we don't have really results from OpenCC, but there's a reason. Oak Ridge has a contract with Mentor Graphics to deliver GCC, OpenCC through GCC for Frontier, but they check mainly functionality. HPE is supporting OpenCC version 2.7 for Fortran. It's quite old, but they will not support OpenCC for C++. So we are not really working towards to have OpenCC code except Fortran in general. However, I saw the CLAC. CLAC is from Oak Ridge. It's a research project. It's about OpenCC for LLVM. It's only for C. Fortran and C++ come in the future probably, but also CLAC can translate OpenCC codes to OpenAP. I have done some tests. It's promising, not perfect. And here again, I have a pragma about how SCC loop, etc. works. There's also, sorry, there's the automatic playing the automatic transition slides. So the vector length and the number of workers can be also tuned here for AMD GPUs. Now the Alpaca is a kind of new framework. It's a library, abstraction library for parallel kernel acceleration. Enables an accelerator agnostic implementation of hierarchical redundant parallelism. It's a user can specify data and task parallelism at multiple levels. In addition to grids, blocks, and threads, Alpaca has an element that represents an n-dimensional set of inputs that can be it's amenable to vectorization, so you can really go for really low level to tune, and besides the platform during the compilation, you decide which platform you plan to use. CUDA, AMD, etc. And also the CUPLA is a C++ user interface for the platform-independent library. It's easy to port to CUDA codes and supports HIP CUDA, TBB, OpenAP, SYCL, etc. Now, let's talk about workflow. As I don't have a laser point here, let's go from the top. This is when there's no, the application has no GPU. So if you go to the right arrow as you see it, you can use libraries if they support the programming language that you use, like Alpaca, SYCL, Cocos, Rasa. If you go in the middle, the question is, does it have OpenAP? If the answer is no, you can use the reveal tool that's provided from Cray to port, to find the loops and insert the pragmas for OpenAP for CPUs. And then you go on the left from this bracket to see to port to OpenAP to floating for GPU. So you have the OpenAP code and you add the pragmas for the GPU part. Now, if the performance is good, perfect. If no, profile tune OpenAP calls and data transfers. Now, there is the option that you can port the non-good performing kernels to heap. So to have OpenAP and heap, but this moment you have to have separate files for this, compile and link at the end. You can have in the same file and heap and OpenAP. And so if you want to go to heap, if the code is C++, profile, identify kernels and tune to heap and port and tune to heap. If it's Fortran, then you have to profile and heap and identify the kernel and use a heapfort. Heapfort is a special library that will write the interfaces to use it to write code Fortran and C interfaces to call C++ kernels, etc. And of course, on the left arrow from the top, if you are really advanced, you can say, I don't care for OpenAP, I'm going directly to heap. The question is how many FTE will take, because it's a lot of effort to port everything to heap if you have OpenAP code, for example. And then it's about when you have GPU codes, then go on the right arrow, it's again the same, use Alpaca, SYCL, Cocos, Rasa, depending on the programming language. If you go to the OpenCC box, we have three options almost, Cray, and Cray will support only Fortran. So if it's not Fortran, you don't need to use a Cray. Now, the CLAC and FLAC is the OpenCC for LLVM, for C and Fortran. They are not ready, it's research projects yet. I'm not sure that how good it will be, but we can try it. And third is a GCC that is provided by Oak Ridge and a Mini-Metal Graphics collaboration. But performance maybe is not the best. And so basically, if the performance is good, perfect. If no, the question is if you want to port OpenAP, because usually you port OpenACC calls to OpenAP. If no, profile and tune the OpenACC calls. If yes, port the OpenACC calls to OpenAP. Usually there is some tutorials that they say this pragma maps to this pragma. And also you can use the CLAC or flag that could help you to port the calls to OpenAP. Now, if the code is in CUDA, if it's C++, the Hipify tools can almost do it automatically for you. We have done a lot of trainings for users that they work really good. If it's Fortran code, use HipFort and prepare the kernels. There is a procedure that have identified to other work how to do that. And again, always it's about the performance, if good or not. And if it's no, fix a code if any issue. If any that was not converted to heap, do it. Profile, use the heap libraries. There are many libraries like heap blast for blast, etc. Don't try to implement everything yourself. Now, benchmarks and applications. One is the BubbleSim. BubbleSim is a memory-bound benchmark with many programming modes implemented with 5 kernels. And I have them the pattern: add, multiplication, copy, triad, and dot. Dot is a reduction, and I like the dot because usually it's more tough. We use the default problem is 2 in the power of 25, FP64 operations, and 100 iterations. And we're evaluating BubbleSim version 3.4 this commit. We track the commits to be sure that we can reproduce stuff. And also in this work, we present for first time results with Alpaca backend for BubbleSim that was implemented for this work. Also, we use application, the mini Buddha, I suppose is pronounced. It's a benchmark that was released during IASM last year. It's a mini app called Mini Buddha from the Bristol University docking engine. It's a kernel for a drug discovery application that's compute bound. So Buddha predicts the binding energy of the ligand with the target. However, there are many ways this bonding could happen, and the variety of positions and rotations of the ligand relative to protein known as poses are explored. That's why we explore a lot of poses here. A number of properties are evaluated. It supports various programming models, but we do evaluate CUDA and heap. We use a version of this commit. Both BubbleSim and Mini Buddha support many programming models, such as heap, CUDA, OpenAP, offloading, SQL, OpenACC, and Cocos. And we have results for all of them except the OpenACC part, basically. Now, methodology and hardware. The compiling basically was quite easy to support whatever the instructions they gave us. We have to declare only the different hardware targets for AMD and for NVIDIA. We execute 10 times and plot the box plots and tune where necessary based on the number of compute units of the GPU and away from the RAM. So we use the NVIDIA V100 basically with 32 GB memory and 900 GB per second memory bandwidth. And we have here the threads that we can read the stuff. NVIDIA A100 also, and AMD MI100. Just to mention that for the FP64 teraflops, V100 7.8, A100 9.7, and AMD MI100 is 11.5. And the comparison software, we really track everything because we would like to know what we can reproduce. So we had access to 2 supercomputers and 1, let's say, cloud. Puchti and Machti are 2 supercomputers from CSC, and AMD Accelerator Cloud is a cloud access from AMD. We use AMD OpenAP 13, LLVM 13, ROCm HIP 4.2, and now there's much newer version. We use NVIDIA SPC SDK 21.7, GCC, a really development version, HIP SQL, Cocos, and Alpaca. So we track everything for reproducibility purposes. Now, the results. Okay, as you see the plot, there is some breaks. We did these breaks because it's easier to visualize box plots instead of having continuous numbers. You could see only straight lines. This is for bubblestem copy kernel. The y-axis is gigabyte per second, and the x-axis is the programming model. So if you see there is CUDA/heap, it's CUDA if it's NVIDIA GPU, it's heap if it's an AMD GPU. And so you can see that the AMD OpenAP has lower performance, and this is like in the MI100 bracket about the AMD OpenAP. And also you can see the default Cocos implementation on bubblestem does not provide tuning options, so we cannot tune the Cocos and add the performance a bit for the V100. Heap cycle, if you got the heap cycle on the x-axis and on the top in A100, has a variation you can see, but it's less than 2%. And Alpaca achieves close performance to heap. In general, MI100 is like 26 to 34% slower than A100 for this kernel, and 15 to 37% faster than V100. And while MI100 achieves 97.8 and up peak performance, except the OpenAP, then NVIDIA A100 achieves 96% for everybody, and V100 is 89 to 98%. Now, for the multiply kernel, for MI100, most of the programming models achieve 96% and above, except OpenAP, while for M100, all the programming models performs close to the peak. However, the V100, the not tuned Cocos underperforms compared to the rest of the programming models. And for MI100, most programming models perform at 21% to 37% faster than V100, except OpenAP, and similarly, it's 25% to 31% lower than A100. So you see, even similar patterns perform a bit different in these cases. Now for the out kernel, the performance of Alpaca programming model is quite close to heap CUDA for all devices with heap cycle following. The OpenAP is less efficient on the MI100 compared to the rest GPUs. And finally, Cocos performance seems to be between Alpaca in heap cycle in this case. Now the Triad kernel, for this kernel, Alpaca performs equally to heap and CUDA with following Cocos and then heap cycle and OpenAP. MI100 is 28 to 32% lower than A100 and 18% to 21% faster than V100. Although MI100 achieves 94 to 99% of the peak, while NVIDIA GPUs is 98% plus. So we can see that the peak performance is a bit slower for MI100 for many cases, and especially the OpenAP is losing a bit in some aspects. Now the dot kernel. Dot kernel is a bit more complicated. Why? Why the performance varies quite significant, and you see more brackets. So in the first V100 bracket, you will see a number in the, not a number, a label in almost a bit right in the middle, MI100. This result was so close to V100 that I couldn't visualize otherwise, just to put the label, this is MI100. And you can see also down MI100 result from OpenAP, because it has actually the worst performance, even worse than V100. Now, MI100 GPU is around 2.6% to 14% faster than NVIDIA V100. What does it mean? NVIDIA SPC SDK performs really great for reductions, while especially for OpenAP, we need some work for AMD OpenAP. For heap CUDA, we define 216 blocks of threads for the A100. A100 has 104 streaming multiprocessors, and this improves the dot kernel performance by 8 to 10%. For heap cycle, we utilize 960 blocks of threads and 256 threads per block to achieve around 8% faster than default values. And for Alpaca, we're able to tune the dot kernel with 720 blocks. 720 blocks means that they have 6 times more blocks than the compute units for MI100, and improve its performance 28% compared to the default settings. And as I said, OpenAP underperforms for AMD OpenAP almost 50% slower than than the V100. So AMD OpenAP needs a lot of development for the reduction part because it's quite behind. Now, the Balazs summary. The The peak bandwidth for the OpenAP programming model is 42% to 94% for MI100, while it's at least 96% for the NVIDIA GPUs, which, as I said, demonstrates that the AMD OpenAP needs further development. For Cocos, the range is 74 to 99% for MI100 and 73 to 99% for the NVIDIA GPUs, where non-optimized version has lower performance, mainly on MI100 and V100. Also, this to identify Cocos is not optimized in bubble stream, which this indicates that needs some learning curve to optimize Cocos. HIP 6 achieves 96% of the HIP CUDA, except for MI100 and dot kernel that achieves 89%, while Alpaca achieves 97.2% for all the cases. The OpenAP compiler performs better for NVIDIA GPUs regarding dot kernel. However, the version that we use for AMD GPUs is not the final product. It's still under heavy development and improving every month. Overall, the Alpaca performance is quite close to HIP, followed by HIP cycle and Cocos, while OpenAP can perform lower depending on the kernel. Now, the results for mini Budem. Now, when I started this benchmark, MI100 was 2 times or 3 times slower than V100, and I was like, why? And started digging more, and we didn't have enough pauses, as I said, the pauses enough to stress the MI100, and started tuning which pauses is the best, because we wanted to use the same workload. So this also stressed the NVIDIA GPUs with a small variation, 1 to 2%. And so the mini Budem provides the signal precision gigaflops, and we observed that the AMD achieves a performance close to 800 by 2%. So although a 100 theoretical peak has better than a 100, in this benchmark is a bit 2% slower and around 26% over V100. Now, we tested also a benchmark, it's called mixed bench, and the MI100 was 1.16 times faster than A100, and both achieved close to their peak performance. So MI100 performs quite good to the signal precision results. Now, conclusion. We presented a workflow for porting applications to Loom supercomputer, an AMD GPU-based system. We benchmark various programming models to understand how efficient they are. So when the users are coming to us to tell them, okay, what is your code, what's your pattern, what programming model to use, we utilize a benchmark and a mini application, which are memory and compute bound respectively. And we saw how the various programming models perform. The first result from BubbleStream with Alpaca backend. It was the first implementation of Alpaca for BubbleStream, and it shows really great results. Yeah, there is a lack of performance on some aspects for OpenAP, and this is a big question. When you have an OpenAP code, it's much easier to go OpenAP offload than going to HIP, for example. But the performance will always be investigated. HIP CUDA performs quite good as expected, and many programming models are quite close. However, the user should be aware about other programming models, and as I said, OpenAP other performance. Finally, programming models such as Alpaca and HIP cycle could be utilized and support many backends, are portable, and for many cases provide similar performance to HIP with a requirement if your programming language supported. So for example, you have Fortran, it's more complicated. These are basically C++ more, I would say. Now, future work. We investigate to identify the issue with the mini Budem as some programming models underperform. We want to analyze OpenCC performance from the GCC and create Fortran compiler, test the new functionalities from the ROCm platform, such as heterogeneous memory management that's coming with the MI200 GPUs. We envision evaluating multi-GPU benchmarks and the scalability across multiple nodes. With Lumi that's coming, we'll be able to use MI250X GPU and compare it with the current GPU generation. Finally, we're interested in benchmarking I/O from the GPU's memory, as we have already HIPified Elbezo benchmark, and also we can identify what I/O patterns are efficient from the GPUs. So that was all for me. If you have any questions.
Thank you, George. Okay, still nobody put anything in a pigeonhole. I didn't see any questions in the chat and among the speakers. So I guess, George, I guess you're off the hook.
Thank you.
So thank you so much.
Thank you.
Our next speaker is Jacob Kopek. His title of his talk is Evaluating Methods of Transferring Large Data Sets.
Okay. It's my turn. Can you hear me?
Yes, I can hear you.
Okay, so good afternoon. I'm honored that I have opportunity to present to you the results of my research. Let me briefly introduce myself. My name is Jakub Kopeć, and I work for Interdisciplinary Center for Mathematical and Computational Modeling of the University of Warsaw. And today I will shortly present you with the results of my research that was conducted in previous year and was focused on the evaluation of the methods of transferring large data sets with the use of common hardware and widely available software. It's incredible how in the last few decades the amount of data created and processed by humanity has grown. The increase is not the adequate word, rather the term data explosion should be used, but more astonishing is the growth of the amount of digital data transferred over computer network. By the way, it's surprising how the internet has evolved from the military project founded in the 60s to the place where people spend large portion of their life. The growth of both amounts of the data generated by humanity and data transferred is exponential, so it's natural that people look for the most effective methods to cope with that data. And this was my main motivation as I decided to evaluate and compare these methods of transferring data sets. And science is the main data generator. The countless computer simulations and research equipment through the world creator gather an unimaginable amount of data. And historically, the particle physics and astronomy were the major generators of big data. And the observatory equipment, for example, Hubble telescope, is even spread across the globe and to the cosmos. And but radio astronomy with Square Kilometer Array project, a radio SKA is a radio telescope project with Square Kilometer collecting area located in Australia and South Africa that will soon generate observational data in volumes never imagined before. And prototype that is designed to be only 1% of the final SKA project is planned to produce 60 terabits of data per second. However, the genomics may steal the title of the biggest data generator with the prediction of using 40 exabytes of software by the year 2025. And among the factors that are boosting the amount of data created by genomics are the constant increase in number of the new high-tech sequencers in production, increasing numbers of new endeavors to catalog all the DNA of plants, animal, and part of microbes, and of course human genomics, sequencing the human genome for the scientific and medical purposes. And the huge data generators are sequencing the genome of cancers that are characterized by unimaginable levels of genetic variations, and the personalized medicine that will focus on the genome of an individual person. All of these projects generate unimaginable amount of data that need to be stored and in many cases transferred over the computer network for an analysis, as the necessary computing power may not be available in situ. As the data transfer might be realized using various hardware and software tools, I decided to evaluate its performance. And the common misconception is that moving enormous amounts of data requires only appropriate network with sufficient bandwidth, but for efficient bulk data transfer over high bandwidth network, we need powerful servers, highly performant file system, and storage. Servers that are able to provide the data at the rate that allows to saturate link efficiently. It is impossible to use 100 Gbps network efficiently if the server provides data at 10 gigs. And the crucial aspect is read-write speed of the storage device that is used in data exchange. The sending side must be able to provide the data at appropriate speed, and the receiving side must be able to ingest incoming data. In the but more than that, the server must also possess sufficient computing power and memory to cope with this transmission task. And this hardware aspect is frequently neglected by developers of data transfer solution, and they tend to focus on the network bandwidth and software solution. And to satisfy the hardware requirements, I used two HP servers that were customized to provide sufficient storage speed and compute power. And when I was benchmarking storage, the servers were interconnected directly with their 100 gigs InfiniBand adapters. But in the network benchmarking part of my test, the Mellanox Metro X InfiniBand extenders were used. The vendor claims that this system is able to provide 30 gigs of raw throughput over 40 kilometers of dark fiber, allowing it to benefit from InfiniBand features. And this most prominent one are hardware implemented random direct memory access, RDMA, between geographically distributed sites. And Metro X system implements point-to-point communication, and the two Metro X bundles that consist of IB switch and dense wavelength division multiplexing transponder are located at the ends of the link. And the IB switch may be connected to local IB network directly or directly to the IB adapter in the server. And unfortunately, during the test, the bundles were interconnected locally within one rack with short fibers, since longer dark fiber was not available at the time of test. And the IB switches were connected directly to InfiniBand adapters of the servers. And the storage performance is one of the crucial determinants that influence the overall data transfer performance. It is common that vendors advertise their products' performance with the number of input-output operations per second or throughput, but often these numbers may be quite meaningless, as this may be theoretical maximal values or the results obtained in the tests that simulate only narrow use scenarios, or even worse, this could be artificially designed tests to obtain high results without any respect to the real life uses of the drives. And the hardware performance is closely coupled with the type of the executed workload. The same drive will perform differently when it will act as a database with a lot of random writes and reads of small portions of data that are spent across the whole medium, than when it will read serial data sequence, for example, streaming long video clip saved in one physical location. In order to evaluate the storage device, one should run the tests that reflect the actual workload that will be run on a given device. As a production workload is not always available or possible to run as a test, people create benchmarks whose task is to simulate various workloads that might be spotted in real life environments. And in 2020, Sven Benner created El Bencho, a distributed storage benchmark for file system and block devices with support for GPUs. And it was inspired by traditional tools such as FIO, MD-test, or IOR benchmarks. And he wanted to create a new, modern, easy-to-use, unified tool that may be used for testing storage systems performance. And what is important, Albencho allows testing the performance of GPU storage access time, and it has become essential nowadays as the deep learning and AI applications operate mostly on GPUs. And there is the storage sweep script created by Xing Feng that is invaluable part of Albencho toolbox, as it provides the user with one button push ability to discover performance characteristics of the storage device with respect to the file size. It estimates the storage throughput by writing multiple hyperscale data sets of different characteristics, a lot of small files, an average amount of medium-sized files, or a few of big files, and present the results in single CSV file or on a graph created with GNU plot. There are other important aspects of benchmarking storage. The most noticeable are the testbed configuration and the file size histogram of the test data sets. And the hardware specification, the benchmark's execution parameters should be as close as possible to the projected production environment. If the target application is host-oriented, then the benchmarking tools should be run on single client host. Analogically, if the target application is cluster-oriented, then the benchmark should be executed concurrently on multiple client hosts. Not only the server specifications should be identical, but to the target ones, but also the whole system should be the same. The storage, interconnects, and the data set structure is very important, as transferring or processing a lot of small files is significantly slower than operating on a smaller number of larger files. The main reasons why I conducted storage sweeps in advance to the rest of the actual data transfer evaluation are that the storage I/O performance may be the one of the bottlenecks in the pipeline of data transmission task, and the sweeps allow for verification if the throughput of the storage service is sufficient to saturate the available network bandwidth. And the results will be was also useful to select the best file system to conduct further research. And these swaps are good start for the test because they bring useful information on how the successive tests may be carried out. For example, which dataset should be used. The first series of tests concerned the local file systems, and here are the results. They help to decide that for the successive test, the XFS file system will be used, as its performance was better in comparison with X4, even though the maximal throughput was similar in both cases. With XFS, the maximal value was obtained for the broader range of datasets. The throughput of 8 SSD coupled in Linux software RAID 0 was almost 8 times larger than the throughput of single SSD drive. So I infer that the overhead of creating software RAID in this case was negligible. I conducted some tests of the BGFS distributed file system that is widely implemented on HPC systems. And as one might expect, the BGFS converged system setup, which essentially means that all the required services, so the storage server, metadata server, and client, are hosted within one physical server, cannot compete with the performance of the local XFS systems. And it's probably caused by the overhead that results from the additional task required from distributed file system, such as metadata synchronization or data replication. And moreover, as all the service were launched on the single machine, they may have to compete for resources which may create further overhead. And in the conducted test, BGFS gave approximately 1/3 of the throughput of XFS. Nevertheless, the distributed file systems are not designed to achieve maximal throughput per server, but to scale. And in BGFS documentation, ZFS file system was suggested as the appropriate base for BGFS when using software rate, and the sweeps showed that the ZFS-based software rate's performance is far below the performance of Linux software rate. And in case of locally accessed file system, the RDMA feature did not influence the throughput, which is not surprising. And hence, in the further test, the XFS file system was chosen as the best file systems for the tests of data transfer protocols. And it is obvious that in this case, the storage service will not be the bottleneck, as 155 Gbps of throughput will easily saturate 100 gigs network adapters installed in the servers. Here are results of the storage sweeps conducted on network or on distributed file systems. The traditional NFS cannot even obtain the throughput of 10 gigs, and the results obtained with NFS using IP over IB, so IP packets encapsulated into InfiniBand packets and sent over the IB packets network are similar. For BGFS sweeps, the LBench was run on the server that was the BGFS client, and the second server that was connected to the first one with 100 gigs Ethernet acted as BGFS storage and metadata server. And the BGFS without using the RDMA feature performed slightly better than traditional NFS, but still it barely saturated 20% of the available bandwidth. The best results were obtained using the BGFS with RDMA feature enabled and NFS over RDMA. And it was NFS using RoCE, so RDMA over conventional Ethernet feature. The RoCE-based NFS seems to perform slightly better, but still the results are comparable. However, in any of the testbed protocols, any of the tested protocols or file systems did not allow to saturate as much as 50% of the link bandwidth. During the transfer test, one server acted as a host while the other one acted as a client. I decided to additionally verify the impact of the AMD simultaneous multi-threading feature on the data transfer. In Intel processors, this feature is known as hyper-threading. During the first test series, the AMD SMT was disabled, and after the first test, it was enabled in server BIOS. I also wanted to verify how the utilization of jumbo Ethernet frames influence the transfer rates over Ethernet. Since majority of the used applications are IP-based, it was necessary to employ, in such cases, the Internet Protocol over InfiniBand, and it is major drawback as it imposes additional overhead and almost completely eliminates the benefits brought by InfiniBand, but there was no other option of evaluating the performance of this application with the Metro X IB extenders. And the first test was the Ohio State University bandwidth test. This benchmark might be used to test the maximum data rate that is sustained in the network, and it measures the bandwidth based on the transmission time of various sized messages passed with non-blocking MPI functions. And here you can see the results of the benchmark. The first observation is the fact that results for all the combinations of parameters are practically the same. As this benchmark is supposed to test the maximum data rate in the network, it's not surprising that the server configuration, so AMD SMT, Ethernet firm size, does not affect the obtained results. Nevertheless, the graphs are ideal way of just visualization the benefits of InfiniBand as interconnect. The maximum data rate of in 100 gigs Ethernet is approximately 55 gigs, which means that the remaining part of bandwidth is used by the service of the Ethernet protocol. On the other side, the InfiniBand data rate is approximately 30 gigs, which means that almost 95% of the available bandwidth may be used to transfer valuable data. And this is exactly the reason why the InfiniBand superiority over the Ethernet. It is able to efficiently saturate the network with meaningful data instead of congesting the fabrics with surplus control data. The next benchmark was Hyper-3, and it is intended to measure the maximum achievable bandwidth on Internet protocol-based networks. And I also decided to check if zero copy method of sending with Hyper-3 has any significant effect on the throughput. And I also checked if assigning the Hyper processes to appropriate CPU socket, so the affinity between the network interface and user process would be guaranteed, would impact the results. And here are aggregated results of my Hyper-3 benchmarks. I noticed that setting the CPU affinity does not seem to influence the throughput while using zero copy method of sending data. Turning on AMD SMT caused a drop in obtained throughputs, and such phenomenon is not seen in the results of the test with jumbo frames. As in all cases, the aggregated throughput achieve approximately maximum network data rates of 55 gigs. There is no evident impact of setting the CPU core affinity between the network interface and user process, as the obtained throughputs was similar to the outcomes of the test conducted with default Hyper-3 parameters. Possibly the obtained throughput was too small to benefit to bring loss from CPU affinity settings. And the last test comprised of transferring 3 data sets using SCP, rsync, which are standard Linux tools to transfer data, BBCP, and MDTM FTP in various testing configurations. The data sets were created using the LBencho. It allows to create data sets containing random data with user-specified hierarchy and size. I created 3 data sets that will correspond to 3 data structures, a lot of small files, an average number of medium files, and few large files. In case of SCP and rsync, the default parameters were used, and BBCP enables user to tune many transfer parameters. Hence, I decided to check if increasing the number of parallel TCP streams to 4 or using a fixed size optimal TCP window instead of auto-tuned one would improve the throughput. And the MDTM, FTP, and Ohio State University bandwidth were the only solutions implemented in my study that support InfiniBand natively without using IP over IB, and are able to utilize its full potential to saturate links efficiently. Moreover, the MDTM FTP is multi-core software that is able to utilize multiple cores with and yes, and the first conspicuous fact is how poorly the standard Linux tools utilize available bandwidth. all configurations, they were not able to provide as much as 2 gigs while using 100 gig Ethernet. InfiniBand, in case of InfiniBand, they used approximately 5% of the bandwidth. Probably this poor performance of these tools is caused by the fact that these tools use OpenSSH with built-in 1 megabyte buffer to encrypt the transferred data. And in order to remove that bottleneck, one should look for the tool that use another encryption protocol or change the data mover to one that encrypts only control channel and sends the actual data unencrypted, for example, BBCP. And BBPC results show perfectly the issue of processing a lot of small files, as the throughput obtained when transferring large files were approximately 8 to 9 times bigger than in the case of the lot of small files. And the best results were obtained during MTDM FTP. Its mechanism of dealing with a lot of small files proved to be successful, as the differences between the lot of small files and large files throughput were not only significantly smaller, but in some cases it seems to disappear completely. And while transferring the large files using InfiniBand, the MDTM FTP was able to saturate approximately 80–90% of the available bandwidth. I was not able to notice any significant impact of enabling AMD SMT feature that would allow drawing any conclusions. And I think that would be all, as I ran out of time. Do you have any questions?
Thank you, Jakob. Let's see. Didn't see any. No questions.
Okay. So
thank you so
thank you
much.
very much for your attention.
Our next speaker is Abdullah Bitar. The title of his talk is Service Function Chaining Design and Implementation Using Network Service Mesh in Kubernetes.
Good afternoon, everyone. My name is Abdullah Bitar, and today I will present our project, a web-based orchestration and service function chaining framework for real-time adaptive networking using Kubernetes. This is a collaboration project between Carleton University and Siena Corporation. The agenda for my talk will be a brief description of SFC deployment in virtual machines and containers, a system architecture for SFC. We will provide a real-life scenario of SFC, some key takeaway from our demo, and then a conclusion and some future work to think of. To start off, I thought it's a good idea just to briefly mention some techniques and concepts behind SFC. First is traffic steering, which is a technique applied to network traffic when additional filtering, modification, or optimization is needed. Basically, steering traffic for the deployment of value-added services. The main idea behind NFV, or network function virtualization, is virtualizing network functions onto industry-standard high-capacity servers that can be located in various locations. This provides benefits such as scalability, flexibility, and cost. And finally, SDN, or so-called software-defined networking. It is a network architecture approach that enables the network to be intelligently and centrally controlled or programmed using software application. This helps operators manage the entire network consistently and holistically, regardless of the underlying network technology. This project is based on the concept of service function chaining, SFC short for, which defines and instantiates an ordered set of service functions and steering of traffic through them. SFC is a mechanism that allows multiple different service functions to be connected to form a chain that enables carriers to benefit from the software-defined infrastructure. Therefore, SFC would consist of physical or virtualized service functions chained together where traffic will pass through before reaching the destination. Some of SFC's benefits are automation and optimization. It automates traffic flow between services and optimizes the use of network resources by leveraging SDN and NFV technologies. SFC plays a vital role in next generation networks by supporting and enabling different technologies such as 5G, Internet of Things, IoT, and edge computing. SFC helps in providing customizable network function services to traffic flows between different networks. SFC concept has been previously discussed widely and deployed over several projects. Specifically, there's a project that has been deployed on OpenStack cloud platform using virtual machines. OpenStack is a free open source cloud computing platform that provides virtual servers and other resources to users. But now there's a new trend shifting toward containers instead of virtual machines. If we closely look at how virtual machines are built over the physical hardware, there is a layer of hypervisor which sits between physical hardware and operating system, as you can see from the picture on the right side. Hypervisor is used to virtualize the hardware. Containers, on the other hand, are like normal operating system processes. They are isolated from other processes by namespace concept. Namespace has its own isolated resources without actual partitioning of the underlying hardware. Also, as you can see from the picture on the right side, each virtual machine runs its own operating system, OS. However, containers share same kernel of the host. This makes it easy to instantiate containers, taking only a few seconds, while instantiating virtual machines take minutes. This brings us to service function chaining. While this means that performing service function chaining for containers imposes a different process than virtual machines. While virtual machines are still a valid option, but recently there has been a shift towards container environment. Virtual network functions have been modified to become microservices referred to as cloud native network function, which incur significantly lower overhead than traditional virtual machines. Therefore, our work focuses on chaining container network function. To perform our proof of concept, we use Kubernetes platform. Kubernetes is an open source system for automating deployment, scaling, and management of containerized application. The simplest way to describe Kubernetes' primary function is container cluster orchestration. Kubernetes is a decentralized architecture based on a declarative model that focuses on defining the ultimate state. Users only describe the application structure to be deployed when using the declarative model. Kubernetes implements a microservice architecture that considers a single application as a collection of small services, each running in its process and communicating with each other with a lightweight mechanism, typically an HTTP service and corresponding API. Kubernetes does not focus on the networking aspect and cannot provide some advanced L2, L3 network features. Kubernetes by itself does not provide a solution, as it concentrates on container orchestration functionality and not service mesh. Here comes Network Service Mesh, or NSM framework, which aims to offer connectivity, observability, security, configurability, and discoverability for lower layers on a network service level. NSM utilizes Kubernetes networking model to perform specific networking function. It is a novel approach solving complicated L2, L3 use cases in Kubernetes. One of NSM's features is supporting policy-driven SFC. And finally, NSM is a community-driven CNCF, or Cloud Native Computing Foundation, sandbox project that is rapidly gaining momentum because of its ability to simplify connectivity between workloads independent of where they are running. In a nutshell, NSM is based on three basic concepts. The first concept is network service, which provides L2, L3 services. The second concept is network service endpoint, which is basically a pod in a Kubernetes cluster that provides a network service application. Finally is the L2, L3 connection between the client's pod and related pods in the cluster. In this slide, I will present the system architecture that includes all related components to perform a service function, chaining, and Kubernetes using NSM framework. We have a control plane, a Kubernetes cluster consisting of multiple nodes. They can be virtualized or bare metal, a forwarding plane, and a monitoring plane. The NSM framework is installed in the cluster. NSM allows individuals to connect to a network service cluster independently of the infrastructure they are on. Hence, a new client would like to access the cluster and deploy a network service. In other words, deploy a service function chain. The client will send a request to Kubernetes. Kubernetes will translate this request to the NS manager, which is responsible for all SFC requests. The NS manager will examine the annotation key value pair in the client's request and then check if the required network service is available. If yes, then the NS manager will deploy the pod, or so-called NS endpoints, network service endpoint. At the same time, a client will be provided a pod. Each pod will have a specific service function to perform. It is important to mention that pods will be composed of at least two containers. One container for implementing NSM control plane functionalities, and the other container implementing the primary service function. The related pods belonging to a chain will be connected together by injecting an NSM interface to the pods. The NS manager is responsible to create a virtual wire between all related pods. Furthermore, WeaveNet, which creates a virtual network that connects containers across multiple hosts and enable their automatic discovery, will make sure the chain is accessible across Kubernetes cluster. While pods are being deployed, other elements in the NSM framework, such as NSM registry and admission webhook, will communicate with the pods. The admission webhook intercepts pod creation request to API server, and based on its internal configuration, it may modify the request and inject specific code in the YAML file. The NSM registry is a list of endpoints registered in the cluster. And the last component is the Spire agent, which is used to provide identity within its implementation. It is used to secure API communication between all clients and servers of the API. The diagram you see is a state machine for a pod in the cluster. After deploying a pod, it will listen to incoming traffic. Before the traffic flow reaches the pod, all traffic will go through a classifier that will read the header and verify if the traffic is following a chain or not. If the traffic flow is following a chain, then packets will be forwarded to containers via the overlay network that was built by NSM. The packet will be processed and then pushed out to the next hop. When it's pushed out, the traffic will go through the classifier again for further examination and sent to the consequent service function via the overlay. If not, if the traffic flow is not following the chain, then the traffic flow will be sent via the underlay network. Today, we will present a real-life scenario of SFC in Kubernetes. Simply, a client wants to watch a video where traffic will pass through some network service functions before reaching the client. The scenario starts by a client accessing a user interface where they will choose a video to watch. This request will generate an application and network intent that will be sent to the backend for processing. The application intent will deploy related service functions, and they are application 1, 2, 3 pods. And the network intent will chain the service functions together by injecting the specific interface. In our scenario, the application pods are video streaming pod, firewall pod, and video compression pod. The video streaming and video compression pods will be injected with a kernel interface, while the firewall will have 2 MIMIF interfaces. After the chain process is done, a wget request will be sent from the video broadcasting pod requesting a specific video to broadcast. This wget request will follow the chain by passing through a firewall and then reach the destination pod. The reduction pod will compress the requested video and send the video back, passing through the firewall and then to the broadcasting pod. Finally, the video will be broadcasted. And just the purpose of to prove the traffic followed the chain, we have Prometheus as a monitoring system to show spikes of traffic flow in some of the pods. And now I will present our demo. The screen is divided into 4 sections. The top left section with the black console is Kubernetes cluster. We will monitor pods creation under a specific namespace, as you can see. Currently, there is no resources under this namespace. Underneath the blue console is the backend connected to the user interface. On the top right side is the user interface, which is the front-end website with the CNA logo on it, where clients will use to interact with. And finally, the bottom right side is Prometheus for monitoring purpose. The first step is the client choosing the video stream. They will go over the video streaming tab, choose video 1, then choose video reduction and broadcast. After clicking on it, this will generate some commands such as creating pods and services. As you can see on the black console, Kubernetes cluster deployed some pods, 3 pods. The first pod is the video broadcast. The second pod is the video firewall, and the third pod is the video compression. Pods status changed from container creating to running, meaning that the pods are ready to be ready for functioning. For the presentation purpose, we will retrieve the actual video size from the video compression, which, as you can see, is 9.1 megabyte. After that, the reduction function for the file has been initiated. The video will be reduced in the video compression pod. Also, for the purpose of this presentation, we will retrieve the compressed video file size after it's been compressed. As you can see, the video has been reduced to 3.4 megabyte. Following the completion of video reduction function, the file will be sent for broadcasting pod. As you saw, the file has been transferred to the broadcasting pod and has been saved. And now the function of broadcasting has initiated. The video, as you can see, will be played on this screen, the requested video from the client. If we go down here, this is Prometheus. A quick summary: it's an open source cloud native computing foundation project that plays a vital role in providing proactive and high availability monitoring solutions. It implements a high-dimensional data model with time series database. Furthermore, it has a powerful, user-friendly query interface for users to access and display the data. Prometheus, for our use case, was used to monitor the hardware nodes, resources, and validate SFC. If we press the on execute button, you will see spikes of traffic flow in some of the pods. We'll go back to the PowerPoint. There are three key takeaways from the demo. Firstly, we have deployed SFC in multi-node Kubernetes environment with network service mesh plugin. The network service mesh plugin helped us to deploy the service function chain. On the other hand, WeaveNet and Prometheus has been applied as add-ons to achieve networking intent. On the other hand, the application intent containers are created and deployed to provide service functions, and each of the customized containers has more than one container network interface. Last but not least, we developed front-end web UI user interface. It simplifies and automates the process of service creation, as you saw in our demo. With just one click, everything was automated up until bringing the video to be played. In addition, the hardware and network usage will be visualized using the Prometheus web model. The operator would easily manage and inspect SFC. The conclusion is based on our research and experience. We would conclude that we have compared traditional service function chaining, or SFC, approach with OpenStack against cloud-native SFC approaches. And we use Kubernetes and NSM with the cloud-native SFCs. During the development of cloud-native SFC solution, we have explored various Kubernetes network plugins that support SFC. There are other frameworks other than NSM that support SFC, such as NFV for SFC. But we found in our analysis that NSM was the easiest to deal with. Based on those comparison, we developed an orchestration and traffic steering framework that allows customers to set up their service function chains dynamically through the web. Service function chaining will be deployed over the cloud-native infrastructures operated by network and service providers, where cloud-native infrastructure providers provides elastic and optimal resource usage. The solution we presented still needs some enhancement. Here is a list of potential future works that could improve SFC in a containerized environment. Adopting cloud-native SFC for big science flow data application can be investigated further. There is a limited number of containerized service functions. Therefore, more containerized service functions containers are needed to be built, created, developed. Adding network analytics to enhance SFC performance by extracting network metrics will provide some data for better performance. And finally, more work is needed to choose the correct network interface for service function chaining. That's all for my presentation. Thank you for your time, and I'm ready to take any questions.
Okay, I didn't see any questions. So let's thank Abdullah again.
Thank you.
So as it's getting late or early, depending on where you are, I'll have a short closing. I'd like to thank everybody for joining us. It was a great session that covered a wide range of topics. I would also like to thank the speakers from all around the world, including the US, Canada, Japan, Europe, and of course, Singapore. Particularly, I would like to thank Prof. Panda and the technical committee for their important contributions. Just a reminder that there'll be 2 more days of events here in Singapore, and I'm sure there'll be something that you may find interesting. Lastly, I look forward to seeing you next year for Supercomputing Asia from 28 to February to March 2nd, 2023. With that, I close Supercomputing Frontiers Asia 2022. Have a good day, night, morning, afternoon. Thanks.